Now that we've created a hash, we can move on to the next stage. We'll show you how to enforce the non-repudiation of a message. To do this, we'll need a digital signature. Let's see how it works. The initial point is a message. As you know, we can compute a fixed length hash like SHA-2 from any variable length message. Once the hash has been successfully generated, encrypt it using asymmetrical cryptography, but don't use a public key. Instead, we'll be using a private key to encrypt the hash. The result is a signature, or a digital signature. It's the output calculated from encrypting a hash function using a private key. What should you do to be able to determine that a challenge has been sent by a specific user? You can calculate a hash from the received message, for example by using the SHA-2 hash function. It's obvious. Now you have the hash of the message you've received. The message was complemented with an encrypted signature, the digital signature. It was also encrypted using the sender's private key. You can now take the sender's public key, which can be accessed by everyone, and decrypt the hash received in the message. There will always be some result. Now you can compare the output from the public key decryption against the output you calculated. If they match, it means that you have proof that the message has not been modified after it was sent. And also, another vital aspect has been established. The sender is unable to dispute the claim that they had sent in the message. They, or someone who had access to their private key. In any other case, decryption using that sender's public key would have produced a different output. This is exactly how the RSA signature works. It's based on the assumption that the private key and part of the public key, the value E, are symmetric. They can be used to encrypt and decrypt data. The operations that are performed using the private key and the public key are directly reversed. This produces an interesting result. Since the private key and a part of the public key can be used interchangeably to encrypt and decrypt data, a peculiar kind of attack can be mounted. If an attacker sends you a specially crafted message and you encrypt it using your private key, the message sender will be able to sign their arbitrary message using your signature, on your behalf. They will also be able to impersonate you. Before we'll show you how this attack proceeds, a few words on what this should mean. If you receive weird-looking pseudo-random strings, don't be so reckless as to instantly encrypt it using your private key. This is the only thing you should keep in mind to prevent an attack of this type. The attack itself works as follows. An attacker needs to generate the message M, a contract, or anything else they want you to sign. Next, the attacker calculates a hash of the message. The next step is to generate the random message X. Then, the attacker generates the message based on the expression Z times X to the power E, where E is your public key. The public key is by very definition freely available. Once you have received this message, you encrypt it using your private key. To do this, you perform the following operation. If you take a look at the encryption process and decompose it into factors, this operation is Z to the power of D times X. The attacker needs only to divide the value that you have encrypted by X, the random message that the attacker knows since they generated it. In this way, the attacker obtains the victim's signature under the message M. A practical piece of advice: don't encrypt anything that is sent to you using your private key. The Elgamal algorithm can also be used to create a digital signature, even if the private keys and public keys used in it are not symmetric. They cannot be used for both operations. The procedure looks as follows. To sign some data, you need to pick a random value k. It has to be the coprime integer from p-1, with a part of the public key. Calculate the equation r equals g to the power k mod p. Then sign the message hash using your private key. All SHA-2 hash functions follow this scheme. The output is the digital signature, a pair of values r and s. You can of course also verify this signature.